In the previous video, we introduced the idea of the rates of chemical reactions, which we called chemical kinetics. And as you'll recall, we really described it as the change in concentration of our products versus the change in time. And we talked about how as time proceeds, the concentration of products increase and then they kind of level out. So down here we have time. And this line is representing the concentration of our products. Well, we can make some similar statements about the concentration of our reactants. The reactants start at a high concentration and they decrease in concentration as time proceeds until we level out. So the yellow line here is looking at the concentration of our reactants, right? So when we were trying to explain this and trying to explain our rate laws, we mentioned that the reason the rate slows down, right, so the rate of this reaction is fast at the beginning, but it's much slower as time proceeds. The reason for this is because the concentration of reactants is decreasing, right? So as we go from reactants to products, as time proceeds, the concentration of our reactants are decreasing, as we can see here. And this correspondingly decreases the rate of a reaction because the rate of a reaction is dependent on the concentration of reactants in some way. So as the concentration of reactants decrease, so does the rate. And we explain this by suggesting that as the concentration of reactants decrease, it decreases the frequency which the reactants can actually interact. So it decreases the frequency of collisions. And this term collision, this word collision, is really important when we think about kinetics, because as it turns out, a very important aspect of kinetics, kind of our thought process for where it comes from, is a theory known as collision theory. And as the name suggests, one of the most important requirements of collision theory is that molecules collide. Molecules collide. Right, so if we have our reactants, right, so let's say we have this compound made of two different types of atoms, and we want it to interact with another compound, right, so this is a different compound, and when they react, we have this kind of exchange, right, so we end up with, let's say, the two hollows together. Okay, so we end up with this compound and this compound, right? So we have an interaction between this atom and this atom, and we break this bond. Okay, so for this to happen, these two molecules need to bump into each other. They need to collide. So that's one requirement of collision theory. Another requirement is they have to collide in the proper orientation. So the collision has to be in the proper orientation. Okay, so if we were thinking about this reaction, right? So we've said already that if this molecule can bump into this side of our other molecule, then this reaction will proceed. We'll give it a little happy face, right? That reaction might happen. But if our purple compound here bumps into this side of our compound, right, it bumps into this atom, then this will not react because the purple molecule needs to create a bond with the hollow blue molecule. Okay, if it bumps into the solid, it won't react. So the orientation of the collision is also important. And the third part is that when the collision happens, there needs to be enough energy. Okay, so there needs to be enough energy for a chemical reaction to occur. All right, so let's think about this one in a little bit more detail. So the idea here is that when we think about the progress of a reaction, so this is reaction progress, and this is going to be versus the energy of the reactants or products, or really any type of compound throughout the course of the reaction. So we are proceeding from reactants to our products. Okay, as we talked about before, this process doesn't just happen, right? So the reactants don't just proceed to products. This doesn't happen. Instead, what happens is we have to transition through a high energy intermediate. So this is called our transition state, and it's at higher energy. So for the reactants to become products, they first have to go through this transition state, and then they can become products. So there's this energy barrier, right? So this is an energy barrier for the reaction to happen, and we call this our activation energy. And we give this the symbol EA. Okay, so this is our activation energy. It's the difference in energy between the reactants and the transition state. It's the amount of energy that our reactants need to have when they collide for a chemical reaction to actually happen. And if they don't have that energy, then the reaction cannot happen. Okay, so according to collision theory, we need our molecules to collide with the proper orientation, and when they collide with the proper orientation, they have to have enough energy to get over this energy bump. So if we take this back to our rate law, we talked about how the rate equals the rate constant times the concentration of our reactants in some way. Right? So the idea that molecules have to collide is really built into the concentration of our reactants. So this part of the rate law is what the first requirement of collision theory relies on. Okay, so the rate of the reaction is dependent on the concentration of reactants because that influences the molecule's ability to collide. So these other two requirements then, requirement 2 and 3, must be built into our rate constant in some way. Okay, and I'm going to introduce another equation here that does a very nice job at explaining that. Okay, so the rate constant is equal to this term A times e to the minus EA over RT. Okay, so we see some familiar things here. First, we see our rate constant. Right, and our rate constant we know is built into our rate law. Okay, we see up here, change colors, up here we see our activation energy. So our activation energy, we said, was the energy it takes for reactants to bump into each other to react. Okay, so this, then, our activation energy is requirement 3. So we see requirement 3 built into this equation. Okay, and as it turns out, this term right here, okay, this is known as the pre-exponential factor. So this pre-exponential factor is where the collision orientation comes into play. So the larger this factor is, the larger this pre-exponential factor is, the more likely it is the molecules will collide with the proper orientation. Okay, so this equation is known as the Arrhenius equation. And the Arrhenius equation is a really important equation to understand chemical kinetics, and it's going to be the focus of the next lecture.